In this video, we are going to talk about the concept of percent composition, which basically is going to allow us to determine the percentage of the mass of a compound that belongs to a certain element in that compound. Okay, so let's start things off with a definition. Okay, so the definition of percent composition is this. If you are given a compound, right, and you want to determine the percent composition for a given element in the compound, we're going to follow a specific formula. The percent composition is the percentage by mass of each individual element in that compound. So if we look at, say, an element A, the percent composition of that element A is going to be given by the mass of that element A divided by the mass of the entire compound and multiply it by 100 to get our percentage. Okay, so we basically have two ways to obtain the percent composition, and the first is to simply take a chemical formula. For example, if we have A, B, little b, as our sort of generic molecular formula here, we can determine the percent composition of A using this chemical formula by simply saying, okay, well, I can look at the periodic table and determine the mass of A. I can look at my subscript, little a, and I can determine the total mass contribution for compound A by multiplying the two. And then I divide by the total mass, which is just taking the number of each element, multiplying by the mass of that element, and adding that up for each element present in the formula. In this case, there's only two different elements, A and B. So this gives us the total mass of A and B in the denominator, the mass of just A in the numerator. Take that ratio, multiply by 100, and you have your percent composition. Okay, so that'll be the first pathway that we follow for solving percent composition problems, right? But of course, this is dependent upon having that chemical formula. That might not always be the case. So another pathway for finding percent composition is to actually use experimental data, and experimental data that can come from a variety of different quantitative analysis methods. One that we'll be looking on later in the course is so-called combustion analysis, and we'll talk about that later on. Both of these approaches will get you percent composition. So let's go ahead and look at an example of how we can use the molecular formula itself to solve the percent composition of each one of the respective atoms. So in this example, we're asked to determine the percent composition of ammonia. And we know it's ammonia. We know the chemical formula, NH3. So the first step is then to determine the formula mass for ammonia. What's the entire mass of a given ammonia molecule? Well, the mass of an ammonia molecule is going to be the mass, total mass of all those atoms involved. So the mass of nitrogen, right, there's only one nitrogen, so it's just the mass of nitrogen plus 3, and remember, we've got this subscript here, 3, right, 3 times the mass of hydrogen. Looking at the periodic table, we find that we get a mass of about 14.01 for nitrogen, 1.008 for hydrogen, add it all up, and we arrive at the entire mass of the ammonium molecule. Okay, now our second step is to plug into our previous definition, the formula in our previous definition for percent composition, and actually determine the percent composition for each one of these atom types. So for the percent nitrogen, we are going to take the mass of nitrogen in the molecule, and remember there's only one nitrogen, we already determined that, so the mass of nitrogen is just this 14.01. We're going to divide it by the total mass of the ammonia molecule, and we will arrive then at our final answer of just under 83%, 82.27%. Then there's, of course, two ways that we could go about finding the percent of hydrogen. We know that the remaining 17 some percent must be coming from our hydrogen because there's only 2 elements present. Okay, so you could, of course, take 100 minus the 82 and arrive at the answer. But what we want to do is, get practice using our formula and our definition for percent composition. So we're going to go ahead and plug in the mass of hydrogen, which is 1.008, multiply it by the number of hydrogen atoms present, 3 in this case, and then we are going to go ahead and divide by the total mass, multiply by 100, and we will arrive at the percent hydrogen. Okay, so this is our first basic example of how we can use the molecular formula itself in a little two-step process for determining the percent composition for any given compound. And so this holds for arbitrarily complex compounds. We'll do it a little bit more complex example here, looking at the aspirin molecule, right? The aspirin molecule here, which is comprised of 6 carbons, 8 hydrogens, and 4 oxygens, right? We're going to be following the exact same protocol, but now we're going to be, given this atomic molecular mass, we're just going to have to do a little bit more work in terms of determining the percent composition for each one of now 3 different elements that are present in the molecule. Okay, but the same pathway. We'll go ahead and start off with hydrogen. Right? We know the molar mass of the compound, so we're going to look at the, in this problem, we are going to use the molar mass, and we are going to assume that you have, say, a 1 mole of this substance. Okay? So if you assume that you have 1 mole of aspirin, we can plug in the molar mass of aspirin on the bottom here, right? Calculated above, right? 180.159. Right? And then we look at it and say, okay, if I have 1 mole of aspirin, right? 1 mole of aspirin means that I have 8 moles of hydrogen, right? And you can count up all the little hydrogens, 1, 2, 3, so on and so forth. Okay? Count up all those little hydrogens, and basically, if you count up every single one of those hydrogens, all right, every single one of those hydrogens, remember there's an 8th one back there. It's kind of hidden behind one of these guys, right? Every single one of those hydrogens, there's 8 of them. So the molar mass of 8 hydrogens needs to be included in the numerator. So you take the molar mass of hydrogen, multiply by the number of hydrogens, we get 8 times 1.008. Take this ratio, multiply by 100, and we find that aspirin is approximately 4.476% hydrogen. Follow the same protocol for carbon. We know the number of carbon atoms, multiply by the molar mass of carbon, divide by the molar mass of the entire compound, we get roughly 60% carbon. And similarly for oxygen, where we have 4 oxygen atoms per molecule, and so we have 4 moles of oxygen per mole of molecule of aspirin. Take that ratio, multiply by 100, and we again arrive at our percentage. And you can always double check your work. At the end of these problems, especially when you had to do a lot of calculations to get there, I strongly encourage that you check your work by basically summing up, right? Summing up all of these percentages that you found. And of course, that total of all the percentages better equal 100%. Okay, so this approach to finding percent composition works great if you have a molecular formula. Okay? Of course, oftentimes in practice, we don't have a molecular formula. So now what we want to do is explore some techniques for how we can determine percent composition using experimental data. In other words, we don't know that molecular formula. We've got some unknown compound here, and we're kind of going to start off doing some preliminary analysis of answering the question, well, what is the percent composition, right, for this unknown compound? Okay, so of course we're going to rely on experimental data in order to do this, and specifically, right, the types of data that we're going to get is basically a breakdown of the relative mass contribution for each one of those elements. So experimentally, you break the compound apart into its individual elemental components, determine the mass of each one of those components, and then use that information to determine the percent composition. So for example, let's say you had a gaseous compound composed solely of carbon and hydrogen, and it weighs 10 grams. It was shown, right, through some experimental techniques that it's 2.5 grams hydrogen, 7.5 grams carbon. Okay, so to determine the percent composition of hydrogen and carbon, all you have to do is take the mass of whatever element you're going after. In this case, we'll look at hydrogen first. The percent composition of hydrogen, we're going to take the mass of hydrogen, right, taken from the problem here, divide it by the mass of the entire compound, take that ratio, multiply by 100, and we get our 75%. Okay? And then once again, we could of course take 100 minus 25 to get our answer for carbon, because we know it's only carbon and hydrogen present. Or you could use that experimental data directly, plug in the fact that you know 7.5 grams of carbon are present, divide by that 100 grams, and multiply by 100 to get our final answer. Okay, and just as we saw in the previous example of aspirin, you know, this same approach applies for larger and larger compounds. Doesn't matter. In this case, if we have a 12.04 grams sample of some liquid, and now we know it contains 3 different atom types, carbon, hydrogen, and nitrogen, we just follow this process repeatedly for each one of the 3 different atom types, right? Mass of hydrogen over total mass. Mass of carbon over total mass. Mass of nitrogen over total mass, okay? And we arrive at our final percentages. All right, so these are our 2 approaches for finding the percent composition for a given compound, right? We either use the molecular formula or use experimental data. So in the case of using experimental data, what we're going to now see in our application section of this mini lecture is how we can use this experimental data, get the percent composition, and use that information to actually determine the empirical formula for a compound, right? We're not going to get all the way to the molecular formula, but this allows us to actually pull out that empirical formula. So remember the definition of empirical formula. The empirical formula is basically provides the relative number of atoms of each element in a molecule. Okay? And so by convention, we're always going to use the smallest whole number ratio. Okay? So we're going to find the smallest whole number ratio that tells us the relative amounts of each atom type. So the steps for determining empirical formula from the mass composition are actually just 2 steps, fairly straightforward. The first step is you're going to use that molar mass to convert the mass of each element into the number of moles. Then we're going to convert the moles of each atom type into whole number ratios. So you got to go from mass to moles, and then mole, and then determine the smallest whole number ratio in those ratio of moles. Okay, so what we've got here, we'll look at our first example, and I think this process will become clear. We've got a sample that's determined to contain 1.71 grams carbon and 0.287 grams of hydrogen. Okay, we want to now determine the empirical formula of this compound. All right, so we're going to start off with the mass of each one of these elements. So the mass of carbon, 1.71 grams, we're going to divide it by the molar mass to get the number of moles of carbon in that sample that we recovered experimentally. Do the same thing for hydrogen to determine the number of moles of hydrogen that are present in that compound. And now, all that's left to do is write out that ratio. Remember, at using these numbers directly, we have a ratio of carbon to hydrogen atoms. Specifically, we know that for every 0.142 moles of carbon, there are 0.284 moles of hydrogen. Okay? And remember, when we're writing out a chemical formula, what we are really doing is writing out the relative ratios of each one of those atoms in that empirical formula. But of course, nobody wants to be looking at an empirical formula that has these decimal places in it. Okay, so what we do then is we're going to come through and we are going to divide by the smallest number of moles to obtain the smallest whole number ratio. So in this case, carbon had the smallest number of moles, so we're going to divide both of these subscripts here by the subscript for carbon, and we will arrive at our empirical formula of CH2. And keep in mind, when you're dealing with experimental data, right, this was just a kind of cooked up problem that I put together here. So the numbers worked out perfectly, but in practice, experimental data, could result in something that say, hey, you get 1.92 or something along those lines. Well, you have to say, okay, 1.92, that's pretty much 2. So you're going to conclude that that whole number ratio is a 1-to-2 ratio. Okay. With this in mind now, we're ready to look at this more complicated problem of moving from percent composition data, as we just talked about, all the way over to an empirical formula. Okay? And in order to carry this out, right, we're going to need to make a little assumption. And I'm going to suggest that what you do, and is follow the same advice I give you whenever we're working with percentages, is to assume a 100-gram sample. Okay, you're dealing with a percentage out of 100, right? Why not assume 100 as your starting place? So in this case, we're going to assume a 100-gram sample. And then we're going to use the percent composition data, our starting point in this type of problem. We're going to use that percent composition data coupled with our assumption of a 100-gram sample to determine the mass of each element in that 100-gram sample. Then we're basically back to what we just talked about. Once we have a mass, we can convert that mass to the number of moles. So mass converted to moles, and then use that smallest number of moles and any other modifications you might have to make in order to determine the smallest whole number ratio of the different atom types. Okay, so I know that looks like a lot. There's a lot of steps going on there. So I think going through an example here will make this a bit more clear. So let's go ahead and look at an example. In this example, we're examining the bacterial fermentation process of grain to produce ethanol. All right, so whether you're making wine or beer or whatever you're doing here in fermentation, okay, this basic process occurs where you're breaking down complex compounds and you're getting a product that is comprised of 27.29% carbon and 72.71% oxygen. Okay, we now want to be able to use just this percent composition data to determine the empirical formula for this gas. All right, so remember, our first step was to assume a 100-gram sample. So that means that if we assume a 100-gram sample and it's 27.29% carbon, then that means we have 27.29 grams carbon and 72.71 grams oxygen. Okay, so this is the reason the 100-gram sample is purely chosen out of convenience, so we can directly change those percentages into gram quantities. Okay, so you could, of course, choose any number you want there. You just come up with more complicated, you're making more work for yourself. So this is basically the easiest path for solving these problems. So we have, under this assumption of a 100-gram sample, the mass of each carbon and oxygen. And now in our second step, we're going to use percent composition to determine the mass of each element in the sample. Okay, so the mass of carbon that we come up with here, basically determine these guys, is just taking the mass of carbon divided by the mass of that compound. And we are coming up with our nice, simple representation for the relative masses, right? The actual masses of carbon and oxygen in this 100-gram sample. All right. Now, once we've calculated the mass of carbon and oxygen, we're now ready to use the molar mass to convert the mass of each of these elements into number of moles. So the mass divided by the molar mass gives us the mole of carbon. Mass divided by molar mass gives us the moles of oxygen. Right? So these two numbers here give us the ratio of carbon and oxygen atoms, or moles of carbon and oxygen atoms, that are going to help us define the empirical formula. Of course, when we write down the formula using these decimal quantities, things look ugly. So what we have to do is divide by that smallest whole number ratio. And we see that carbon has the smallest number of moles, so we're going to divide both by the number of carbon atoms, the number of moles of carbon atoms, and we arrive at our final answer, CO2. So CO2 is the empirical formula that is the result of a gas that's 72% oxygen, 27% carbon. Okay. Now it's important to note here that in this problem, right, it turns out that the empirical formula for this gas is also the molecular formula for this gas. CO2 is the one of the major metabolites, products, or results of this bacterial fermentation process. But in general, this empirical formula is just that. It's not necessarily going to tell us the actual molecular formula, the actual identity of a compound, right? In order to determine the molecular formula, we're going to need to do some more work, and that'll be the subject of a next mini lecture. Okay, so let's do a quick little summary then. What we've seen here is that the percent composition can be determined or is defined as simply the percent of a given element, in this case A. The percent of A is going to be the mass of A divided by the total mass multiplied by 100. Okay? And there's two different ways that we can go about determining percent composition information. We could use a molecular formula, or we could use experimental data. We want to be able to use both. And we also saw how this percent composition data allows us to essentially go back and forth with determining the empirical formula. And what I mean is that if you have a percent composition, we saw how we could use that percent composition in order to determine the molecular formula. And of course, if you had empirical formula, of course, if you have an empirical formula, you could go back the other direction and determine that percent composition.